Good morning. Thanks for joining us today for the deep dive into CNCF CI. My name is Lucina Stricko. I'm here with Denver Williams. We're with Vulk Cooperative doing this project for the CNCF. In this 35-minute session, we'll go through a quick intro of the CNCF CI project. We'll introduce the CI team, the goals, key features, and I'll walk you through the dashboard. And then I'll hand it over to Denver for a deep dive into how we added ARM support to the CI's testing system, some of the challenges, benefits, a live code review, and then we'll go over how are some ways to get involved, and at the end we'll have 10-15 minutes for your questions. So a little bit about Vulk Cooperative. We are a worker-owned software consultancy. We've got 4 worker owners and 5 to 10 associates, and we're located all around the world. We're a fully remote team. We are based in Austin, Texas. Some of us are based in Austin, Texas, where we host 2 meetups, monthly meetups, one on Austin software cooperatives, and the other called Open Source Axes, where we meet up with other open source folks in Austin and throw axes at a target. Pretty fun. You can check us out on Twitter. The CNCF CI team is Taylor Carpenter, myself, Watson, Denver, and not with us today, we've got Josh Smith, Robert Siekman, and Krista Williams. So the CNCF CI project consists of 3 parts: the CI testing system, the status repository, and the user-facing dashboard at cncf.ci. The CI testing system validates the builds and deployments for CNCF projects on their stable and head releases, on x86 and ARM architectures, on bare metal packet servers. And the CI testing system can reuse existing artifacts from the project CI, or it can build artifacts on its own. And then the status repo collects those test results and pushes it out to the user-facing dashboard. Some of the goals of the project include complementing the CNCF landscape and trail map, and that can be found. There's an interactive landscape at landscape.cncf.io. We also wish to promote CNCF-hosted projects and help attract more projects to join the CNCF. And we demonstrate the use of cloud-native technologies on multiple test environments, and support and contribute to a sustainable and scalable ecosystem. We'd love to get feedback from cloud-native end users and CNCF project maintainers. And last but not least, we provide a third-party, unbiased validation of the builds, deploy, and end-to-end test for CNCF graduated and incubating projects. And this is provided as a service for projects, which can be found at cncf.io/service for projects. Currently, the CNCF has 6 graduated projects and 17 incubating projects, and 13 sandbox projects. So we'll go through some of the key features of the CNCF CI dashboard, testing system, and status repo. The first feature, the first goal, is that the CNCF CI project is project-centric. We want to put the graduated and incubating projects of the CNCF front and center. So we're validating the stable and head releases of those projects. We can reuse the build containers from the project CI system. We use upstream Helm charts for the deploys, and we can reuse end-to-end tests that are provided by the project maintainers. Secondly, collaboration. We want to increase engagement with the CNCF project maintainers. We'd like the projects to be able to maintain the project and release details through a pull request. We'd also like to use maintainer-provided Helm charts and smoke tests for the app deploy phase. For the end-to-end test, we welcome contributions from the project maintainers on those. And we wish to integrate the CNCF CI testing system with the project's testing systems on Jenkins, Circle CI, whatever they happen to be using. Thirdly, the CNCF CI project is agnostic and provides agnostic testing. We like to validate projects, builds, and deploys in a configurable test environment. So we support per Kubernetes release. We currently do stable and head. Per architecture, which is currently x86 and ARM64. And we're on bare metal using packet.net. So I'll walk you through some of the key features on the dashboard at CNCF.CI. Here's a quick look. The CNCF.CI dashboard refreshes every day at 3 a.m. Eastern Time. The test environment at the top is configurable. It shows Kubernetes provisioning per release, per architecture on the bare metal packet, and the success is the provisioning stage. The test environment dropdown currently shows 4 available test environment options. We've got Kubernetes stable on x86 and Kubernetes stable on ARM, as well as Kubernetes head on ARM or x86. Earlier this year, ARM joined the CNCF as a gold member. And the CNCF CI front-end dashboard is one way to help achieve the ARM's goal of ensuring that Kubernetes and CNCF projects all run well on ARM-based architectures. You can check that out at CNCF website announcement page. Special thanks to tech journalists for this fun headline. CNCF arms itself with graduated project support. With our latest release 2.4.0, we added ARM support for Kubernetes, FluentD, Prometheus, build, and deploy stages onto ARM. So with that in mind, I'll hand it over to Denver Williams to talk a little bit about the challenges, benefits, how you can get involved, and a code review of how we added ARM support. And I'll see you later for Q&A.
Thanks, Lucina. Hey everyone, I'm Denver, and I'm one of the original co-founders for the CNCF.CI dashboard, and I've been working on adding ARM support. So I'm going to give a bit of a talk about some of the challenges we faced when adding ARM support, what were some of the easy things or benefits that we had, and then how we went about implementing it, then do a bit of a live code review. So one of the first challenges we ran into was Kubernetes, because we needed to do that first. And if you want to do ARM builds on Kubernetes, you need to enable it hard-coded in one of their files. And if you're using release.shell, everything in that repo has to be committed before you can do a build. And that presents us with a problem when we're doing head, because if we need to enable ARM, we have to do a commit, and then we've diverged from what's upstream, and then we'd be showing our own version of the commit, which wouldn't match up. So we had to move away from using the release scripts and create our own. FluentD was another project that was a little bit challenging because it's written in Ruby, so there was no cross-compiling off the bat. So we had to switch to using an emulated build on an AMD 64 box. So there's QEMU static, or the QEMU binary, and you can configure that. So when you're on an AMD 64 system and it sees that you're executing an ARM binary, it can hand it off to QEMU and process it in the user space, which allows you to build an ARM64 binary on an AMD 64 machine. Envoy was probably one of the most challenging projects we added support for, because they themselves had only just got ARM support working probably in the month before us. So the first problem we had with that was Bazel. It's written in Java, and no one from the Bazel release team is currently publishing ARM64 artifacts, so we had to build that from source before we could do anything else. And it's written in Java, so QEMU emulation to build it on an AMD 64 box, not going to happen. There's a massive amount of bugs with that, and I mean, I'm sure you could get it working if you wanted to spend a couple of days debugging QEMU logs. So we instead had to build on a native ARM64 machine. And then now we could build Envoy, but there's no documentation. There's about 2 issues that they've tracked it in, and that's about all you've got to go off. But what were some of the benefits? What were some of the projects that or items that we found surprisingly easy when we were adding ARM support? Well, the good news is Kubernetes doesn't require any configuration changes when you're deploying with ARM. So our provisioning tools that we were using, all they needed to be told to do was use our ARM binaries that we'd built, and everything from there worked out of the box. Projects written in Go are very easy to deal with because Go has really nice cross-compiling support, so it's generally the process of adding a flag, and you've got ARM64 builds. And CloudNativeCon and Prometheus make scripts in their repositories already had support for that, so you could go make ARM and you'd have binaries to deploy. So I'm going to do a bit of a code review now and go for each project and show some of the parts that were easy to implement and some of the parts that were really difficult. So Kubernetes, we now have a menu here that shows both stable ARM and head ARM, and we're actually currently working on an update to this that splits this out, so we have an independent column for the release and then a separate column for the architecture. And then the Kubernetes configuration file can be found here, and this is all public, so if anyone wants to contribute open pull request issues, then feel free. So our configuration files, we're having to support both builds in the same GitLab configuration file, which is a bit of a restriction on the GitLab side, so we had to do conditionals. If the architecture is ARM, then do some different steps. And can everyone see that all right? Is that? All right, cool. All right, so, and this is where I was talking about we had to move away from the Kubernetes release scripts to actually do this. So on line 43 here, you can see we're using their libraries to do the build, and then appending the platform we want to use, Linux ARM64. And then we write their config out, generate our own release type script, and on line 52 we run the build. And then for the container job, this is where we take those binaries and we package it into a Docker container for Kubernetes, and then publish a release file that we can give to our provisioning tool so it knows what artifacts to deploy. And here is the nasty bit that we have to actually do a sed on hacklib Golang to set the version of Kubernetes we want to publish. So we pretty much disable all architectures except ARM, so we can do an ARM build. And then we generate the script necessary to publish the images, and then on 122 we run that, and that will go through and take the binaries built in the previous step and then publish them to a Docker registry. So the next project we got to add support for was CloudNativeCon, and this was a fairly straightforward project to do because it was written in Golang, and they'd already done most of the heavy lifting in their make and release scripts. So we have a similar conditional statement here, and that's pretty much the magic there. System, we want to do it for Linux, and the architecture, we want to do it for ARM64. And then when we publish the artifacts or package them into a Docker container, we reuse their existing scripts to do the make, so we actually even share the same commands down here for the build for both ARM and AMD64. So the next project we added support for was Fluentd. So this project was a little bit more involved because it was written in Ruby and they currently hadn't added ARM support upstream. So we had to hack their existing CI deploy tools a little bit to have the builds work successfully for ARM. So here we have a similar conditional statement. Is it ARM? And if it's ARM, we want to enable a map here, which tells when you run this on an AMD 64 system, it enables configuration on that system. So when it receives when someone tries to execute an ARM64 binary or ARM64 executable code, it realizes what it is and then passes it off to QEMU so it can do an emulation and process it. And then we just use their normal make scripts from that point on to publish and compile the gem. And then we move down to the container stage where we want to install that gem in a container. They have their own upstream Docker files to do this, but there was no configuration to support ARM on the fly, so we had to do a few changes and put this line in so it would use an ARM container as a base image. And once that was available, it would go through and install an ARM gem for Fluentd, and we could publish it and run it on an ARM64 machine. And then the project after that we added was Prometheus. And Prometheus was another very quick project because they've already implemented ARM tooling for their builds, and it's all documented and it's very easy to follow. So here we've got that identifiable ARM64 block where we say these are the steps we need to do in addition to build on ARM. And what this involves is just disabling all other architectures except ARM64. And Prometheus uses a build tool called Promu, and it just reads this YAML file, promu.yaml, and sees what architectures are enabled. And if the only thing there is ARM, then it will just build that. And then the important parts here is the make promu and the cross build, which outputs a Prometheus binary that's compliant for ARM64. And then the container, there wasn't really anything here that had to change. We just leveraged their existing Docker files, and they supported the binaries that had been published. And then the most difficult project was definitely Envoy, and on the production version of Dashboard, it still says NA. The work is actually done, and it's something that we'll be working to promote there in the next week. So if you take a look at the dashboard in the next week or so, you should be able to see Envoy running for ARM. And this is the configuration that I'm least impressed about. It's full of SED and not too wonderful. So for this, one thing you'll notice that's a little bit different is we've got completely independent jobs for ARM because we have to do this on line 33. We've had to set a tag and tell it to build on a physical ARM machine. And then the build scripts have absolutely no support for ARM, so we take their existing scripts and we tell it to use a base image that has an ARM version of Bazel installed, and then remove a whole bunch of packages and commands that don't exist in ARM repositories. And then the compile is at least a little bit easier. We can just run the normal command that anyone would run if they were building Envoy in an AMD 64 machine. And it publishes. And then the package to package it into a Docker container was a little bit more involved because their make scripts for that didn't support ARM. And the bigger one here is that they use glibc for their Envoy, for their Alpine base image. And see if I can find that in here. So it's this line here. So we need to use glibc Alpine for the base image on ARM, and Alpine doesn't publish any glibc binaries, packages for ARM64, so you have to go build glibc from source and package it and install it, which is a real nightmare. But we've done that, and the work's open sourced upstream, so if anyone wants an ARM version of glibc on Alpine, then you're welcome to take a look. So how to get involved? If you're interested in collaborating, we're still needing to add support for a lot of incubating projects, and if you're an incubating project here, from an incubating project and would like to contribute, we'd love to work with you. So we're currently in the process of refactoring CNCF CI to make it easier for external parties to contribute, especially projects. So those configuration files we were looking through, so that we want to make those more public and ideally fully maintainable by projects themselves, so they can directly manage that themselves. And projects have their own CI systems. So the perfect world for us, where we're aiming to be in the next half a year, is leveraging existing CI systems. So instead of managing a configuration file for that, be able to integrate your existing Circle CI or your Jenkins builds with the dashboard and show a status there. And then we can augment that data and then do a deploy using the artifacts you produced from your CI system. We have a working group on the 4th Tuesday of every month, so if you're wanting to get involved, that'd be a great place to show up. And the next meeting is on June the 25th. And we also have a public mailing list. So if you have any questions, feel free to ask there or create an issue on GitHub. And we're also on Slack. So that brings us to Q&A. Does anyone have any questions?
So you mentioned for Fluentd that you run Fluentd with QEMU as AMD64 on ARM, or it was the other way around, and it just seemed like it was backwards to me, because you want to test that Fluentd can execute on ARM64, right?
Yeah, we test that it executes on an ARM system, but we don't necessarily want to do the compile on an ARM system, because we have to do our runners. When we do jobs, it's very difficult, and this is a bit of a GitLab limitation, to isolate, to do the build on an ARM machine or an AMD64 machine. So we're kind of stuck with one system type. So for the build, we want to do the builds only on AMD64, which means if you want to publish an ARM binary,
you're using QEMU as a cross-compiler on an ARM machine.
Got it.
To cross-compile back to ARM, to an ARM binary, yeah?
Yeah, you've got
it. Yeah.
And then when we do a deploy, we deploy it to a real ARM system.
Cool.
Have you encountered any differences between the artifacts if you cross-compiled it, if you have the QEMU compile variant, and if you compile it on a real ARM64 machine?
Not that I've noticed. It's not not once the binary's been published, and they both run on ARM64. A real ARM64 machine, and I've noticed no difference. The main difference when you're using emulation is you may run into problems during the build process, especially if you're building something like Bazel, which is Java-based, and Java does not like being emulated. So I'd say the main differences you'll find are during the compiling process of the artifact.
Did you experiment with C or C++ projects on the side?
No, I haven't. Envoy would have been the C++ one, but I ran into the Java issues long before I got to actually compiling Envoy.
Thanks.
Any other questions? Great. Thank you so much. Appreciate your feedback and attendance. We have stickers and buttons, if you would like, for Vulk Cooperative and our little octopus guy. And we'll see you again soon. Have a great conference.